So in this video, we're going to talk about static pressure. We've done a lot of videos and classes on airflow, and one of the things we talk about in airflow classes is the total static pressure of a system. A lot of people don't understand that most systems are designed for a 0.5 static pressure. So when you get a system where you're running up to an inch or more of static pressure on a system, you could run into problems. So in this video, we're going to talk about that. So first of all, let's see what static pressure does to a blower motor. Now, PSC motors have been around for a long time, but they are being phased out. So a permanent split capacitor motor is a non-communicating motor. It has 2 to 4 speeds that's designed into the motor windings, and the high voltage from the control board to the motor is usually what runs the motor with a capacitor included. And higher airflow reduction takes place as the external static pressure increases. You'll notice in this example that at a 0.5 static pressure, you have 835 CFM. As the static pressure increases, you start losing that CFM. So at an inch of water column, you have gone from 835 CFM to 195 CFM, which is a 65% decrease in the available CFM to that system. Then we get into the ECM motors that are available in some of the furnaces and fan coils. So the FCT, or fixed constant torque ECM motor, is a non-communicating motor, has 5 speeds that are programmed into the motor. Low voltage, or 24 volts, from the control board to the motor controls the airflow, and airflow reductions as ESP increases with the constant torque. So you'll notice that at 0.5 we have 1,445 CFM available, and as the static pressure increases, as with the PSC, and you get up to an inch of water column, that CFM has decreased to 995 CFM available, which is a 21% decrease. Then we have the VCT ECM motor, which is a variable speed, constant torque ECM motor. It's a one-way communication. The variable speed motor speed selections are through dip switches, and the airflow can be adjusted from -7% to +15%. The control board communicates torque to the motor based on the dip switch settings. Again, as the external static pressure increases, we see a reduction in the CFM that's available. So at 0.5, we have 1,445 CFM available, and by the time we get to an inch of water column, we have 910 CFM, which is a 25% decrease. Then we get into the VCA ECM motor, which is a variable speed, constant airflow, and we get a little bit better performance out of this motor. It is a fully communicating 3.0 version ECM motor. Its variable speed communicating motor maintains a constant airflow. Airflow selection is through the wall control. Constant airflow even as the external static pressure increases. The control board communicates to and from the motor to maintain constant CFM. So because this is a two-way communicating motor, it increases the speed of the motor to try to keep up with the static pressure. But again, at a 0.5, we have 1,320 CFM available, and at a 1 inch, we have 1,315, which is better, but we're still losing ground with it. So you'll notice on the data tag of most units, you're going to have your maximum external static pressure, And as we said, most systems are supposedly to be designed for a 0.5 static pressure. So when you're designing your duct system, or when you're working on a job that has a problem with airflow, you want to take your external static pressure and see what it's at to try to find out what kind of CFM you're maintaining. And then you may have to make some adjustments to your ductwork to get better performance out of the furnace or the air handler. Let's look at some things that you can do. One of the things that most technicians or installers overlook are the fittings that you use in your ductwork. The next two examples are pages out of the Manual D that show the different fittings that can be used and what their equivalent length is. Equivalent length is a real killer on ductwork. You'll notice in this first page the 4G and the 4J. If you use a 4G fitting, the equivalent length of that fitting by itself is 80 feet. So by putting that fitting on the end of a run, you have just added 80 feet to your ductwork. Instead, by using fitting 4J, your equivalent length reduces down to 30 feet. A little bit better. So try to consider this next time you try to size your fittings for your job. Here's another example using a 4K or a 4L. Again, the 4L is an 80-foot equivalent length, and the 4K is a 30. So again, consider your fittings and the equivalent length that they add to your ductwork. So what does equivalent length do for you? Well, it lengthens your ductwork. In this example, we have flex duct that is run from a unit down to a fitting. You'll notice the distance when measured with a tape measure is 12 feet. But when you add two 45-degree fittings plus the 90-degree where it turns into the fitting, that 12 feet distance turns into 124 equivalent length. Another thing you need to take into consideration is the effective length of your supply ductwork. How many of you have seen this type of a fitting where you come off the furnace or the air handler and immediately go down the ductwork? I've always said in most of my classes that air is stupid. So when air is coming out of an air handler, it's not going to take a right turn down the ductwork. It's going to continue straight ahead and hit the top of the ductwork and do some bouncing around and some turbulence before it decides that it's going to need to go out this way in the ductwork. A fitting like this at a 0.5 static pressure gives you 120 equivalent length to that system. If you taper it, just do a 45-degree on the transition, at a 0.5, it drops that 120 equivalent length to 35 feet. And if you put vanes or a different type of transition in it, you can drop it further to 20 equivalent feet. Which one would you want to have on your job? Then looking at some return setups, you may have seen returns like this, where you have quite a bit of turbulence through the ductwork because of the straight transitions. This adds 30 equivalent feet to your ductwork. But by sloping it and putting a 45 in it, you can reduce it all the way down to 5 feet, depending on your slope and the transition. So if you're designing ductwork, or if you're a technician working on a problem job, always consider your ductwork and your fittings and your equivalent length, and try to keep your static pressure as low as you possibly can.
Go to arefco.com for more videos, like, subscribe, and check back every week for new videos.